Okay, to finally wrap up Laplace transforms, we're going to be discussing about one main application of Laplace transforms, which are important to both electrical and mechanical engineers. And that is the entirety of control systems. Well, here's the standard model for the control system. You have some kind of input. Going into a summer, and it outputs an error function. But to kind of see why, but to kind of see how, we must first finish the picture. Here you have G C of S. For now, we'll ignore what it means and we'll explain everything once we see the full picture. So the famous picture, okay, we have this part right here, minus and plus. So this is the famous picture of control systems. And actually, it's pretty much the start of control systems. You can ask pretty much anything and everything about it. Looking at stability, looking at how the system behaves under different conditions, you can pretty much look at and analyze almost everything through the scope of this picture. This is the picture of control systems. This is pretty much what is control systems in essence. It is looking at some kind of system with feedback and making sure that we get the desired outputs. We have our input, which is compared through its feedback, which outputs some kind of error for the controller, and this is called the controller, and this is called the plant. For the controller to make corrections for the plant to achieve desired behavior. Now, if you look at everything, you notice that we have a lot of Laplace. I mean, all these functions are complex frequency. And all of these are attributed to the property we discussed previously, convolution. Given two time functions, the Laplace of them is their multiplication. And this property fundamentally establishes modeling for any kind of control system that we desire. It doesn't actually have to be electrical, although due to my background, I discuss it in the scope of electrical. It could be mechanical, it could be chemical, it could be thermodynamic, but it doesn't really change that it's in fact a system in which we want to correct errors and find a desired output behavior. So that is the idea. And, in order to really and properly have a feel for control systems, an extremely strong mathematical background on top of being good in Laplace transforms, and hopefully the viewer has demonstrated to themselves this case, helps you in control systems. But not only in control systems. It could help you otherwise to solve circuits in the scope of Laplace. Any kind of system in which they describe it as a linear time invariance, or sometimes they call this LTI, we can apply Laplace on and find something about it. Input, output, feedback, forward, doesn't matter. We can find something. We can find a differential equation model for it. We can find the Laplace transform of it. We can find stability. We can find what's called its root locus, its frequency response with Bode plots. And that is the kind of the study in the field of control systems. And for the viewer, if they are somebody who are pursuing electrical engineering, mechanical engineering, chemical engineering, thermodynamic engineering, it is recommended for the viewer to have a course similar to control systems to try and understand and to try and have a feel for the power that Laplace transform presents to the viewer. We wrapped up Laplace transforms by first discussing its definition, by discussing the validity of different Laplace transforms acting on different time functions. We discussed about how to do Laplace transforms and how to show that some of them aren't valid Laplace transforms. And we also talked about all the Laplace transform properties, the other Laplace transform properties, and why they would be useful. Now, finally, we wrap it up by talking about control systems. And that this picture, as drawn here by this block diagram, is the main basis of control systems in which we can ask anything. We can ask about feedback. We can ask about feed forward. We can ask about comparison, the error function. We can ask about steady state. We can ask about transients. Anything we would like to know about a system, we can understand its behavior through looking at its feed forward and its feedback. Additionally, we can also look at it in its closed loop transfer function, which is just the entirety, which is just the relation between the output and the input. And we also wrapped it up by finally discussing that any kind of function that's linear time invariant, and the viewer is free to research and to get a feel for what this term means. Whenever we have an LTI system, we're able to apply Laplace and define something about it. Differential equation model, we can find initial conditions. Anything that we desire, we can probably find it. I hope that this was informative to you, and thank you.